Good morning. Hi everyone. Whoa, our everyone is just a few people this morning. But it's because it's Wednesday. Let me arrange my screens really quickly so I can see you guys. Okay, I see the chat. Good morning, Saja. Hi, Robin. Good morning. Hi, Isla. Esmeralda. Good morning. And Gary. Good morning. Hi, Bradley. I see you all joining us, and more people are coming into the room, so that's great. We'll have more people. Good morning, Nathan. um, yeah, we've made it to Wednesday. Good morning, Destiny. Hello. We've made it to Wednesday, one day away from finishing the fourth week. We're almost there, y'all. This would be something like maybe a week or two before Thanksgiving if we were in the normal fall semester. So pretty far ahead. And
Sometimes,
huh?
sometimes I wish we only had 5 week classes, like that was the only classes we had. Because like it's easy to focus in a short period of time. The material stays new and fresh, and like you don't forget anything. Like in the regular semester, my issue is that I forget the stuff by the time we have the tests.
Yeah, when you're in 5 weeks, you're really immersed in the study, right? And Saja
Yeah.
too.
And it's easier to have a singular focus. Yeah.
And let me say that this is, I don't know if this is true. I think it's true. You guys tell me. I think this is very specific to these STEM classes. Yeah. Good morning, Mehmet. Because not everyone feels this way about winter and summer session classes, and in fact, many counselors don't agree with these type of classes. Maybe some of your counselors may have told you not to take physics 101 in the summer or winter, but once you work with a counselor that is a specific that works with the science faculty, like our counselor does, Kimberly Wicker, um, then she better understands the scheduling issue for STEM majors and working our way up to a more rigorous schedule and a more rigorous unit load that is just simply required of our major. It's just part of studying in the STEM classes. Oh yeah, I see some comments here. So Saja, you also do better than these classes. Our dean in the sciences has a background in engineering, and her focus is now education, but her background is in engineering, so she was very supportive of us scheduling these winter summer classes. Oh, Noah says if you get quarter classes at some universities, you get 10-week courses. Yeah, on the quarter schedule, you're usually on about 10 weeks. That's how it is at most of the UCs. And let me tell you, there are no breaks for science students. You have, as a physics major, I think I had a midterm every 3 weeks. Every 3 weeks, a new midterm, and it's like you're just getting like one after another. Yeah, you're getting it's like whiplash, and you have to, get better in a few weeks. Good morning, Daniela, and yeah, the math classes. I also agree. And winter's a good time for GE courses. Yeah, you can take 2 or 3 GE courses, but I really recommend for you guys to leave the GE courses for second summer session if you have that space to, or
Adding inside
sometimes,
the general semester.
yeah, in the general semester I would recommend maybe one or two, because um, the ones you want to take right away in the fall and the spring are English 101 and English 102, or whatever is equivalent at your campus. And then after that, you really want to try to group them into places where you cannot take a science class, because as STEM majors, you have to bounce around campuses. You have to sometimes take classes out of order. It's just all over the place. Yeah. And such is the life. I'll tell you, it's not that much different at the university level. You have to bounce around and try to stay on track with a sequence. So um, yeah, you adjust. Yeah. Oh, and that's very much the case. Taking classes at 3 to 4 colleges, we and for some you're lucky when you find a certain campus that teaches a class that others don't. Like we send all of our science students to West LA to take the discrete math class, especially
Oh
for you
yeah,
computer science. For you computer
City I think
science, maybe.
has it too.
I didn't hear that.
I think City has that too.
Yeah, I think they do. I'm not sure, but we've always sent our students to West because of the experience that they've had.
Is
So
that methods of discrete mathematics?
yeah, it's a discrete math class and it would be offered on Saturdays. So it was really great for many of the students to take that. So that's what we recommended. That's, for some places you'll have to find the class wherever you can take it, right? For engineers, there's a course that is the economics of engineering that only is offered at ELAC, but it's offered at the same time as my materials of engineering classes. So we kind of switched it. At ELAC, it's offered in the fall, so I teach my materials of engineering in the spring, because I want you guys to be completed, right? To take all those classes. So yeah, you gotta you gotta figure out where you can take it, and um, a lot of times your instructors are a really good resource for figuring out classes and schedules like that. Daniela has a comment. She says, I noticed the prereqs and the equivalent CSE courses are
Exactly.
different depending on the community college you go to. So it could add courses to your course history. GPA gets affected too, but it's not too different, I think. Daniela, that's exactly it. For those of you who are here, use the raise hand feature, which you should see if you go over your name. How many of you took Physics 11? Okay, I see. I know Randy took it. I see Esmeralda took it. Maybe some of you not raising your hand took also Physics 11. Um, so at Trade Tech, we don't have that as a prereq for Physics 101 because it truly is an introductory course that shows you a little bit of everything without any calculus. And we think as a STEM major, it's more important for you to get right in it. Get right in it, jump into your courses. But at places like ELAC, Physics 11 is a requirement for Physics 101. So if you take Physics 101 on their campus. But just like Daniela says, Physics 11 won't transfer and it won't count towards your transfer GPA either.
That's
Oh, uh-huh.
that sucks. I didn't know that.
Yeah, and
Can it
if
count as like a non-major like science class, like a physical science or something?
no, it won't even be relevant for you because your IGETC, if you fulfill the IGETC, will be um, will you'll use Physics 101 and 102 and 103 for those requirements, but Physics 11 won't count towards your major GPA. Yeah,
But it will
but
like
again,
will it count as like a credit for a general elective or something like ran nothing? See, I wish I'd have known that. I wouldn't have taken it because I already took Bio 3 too.
I that's another one. I don't recommend STEM majors, physics or engineering majors to take Bio 3 until you're at the very end because there's a science IGETC that you want to focus on. And Bio 3, if you can get to it, then you get to it. But it is much more important to get started with physics and calculus. So for all of you out there, your priorities are math, physics, major courses. That's your order of priority. Starting because calculus gets you into physics, physics gets you into engineering and major courses. Yeah, so let me see some comments. Owen says, I kind of messed up. I realized I could have taken physics for bio majors and only needed 2 semesters because the series is 3. Yes. Oh, and that's totally true. You could have taken physics 6 and 7, but many schools, especially if you're going pre-med at all, are are falling back to the calculus based series. So I think you did yourself a favor by taking this series instead. Yeah. Yeah, the chem classes. Also, guys, on assist, if you see a course that isn't transferred yet, but you know the classes match, you could let me know and I could confirm it with you because assist isn't updated for every school and every class and every college. So um, yeah, it happens too. So if you have a question, just let me know. Um, Let's see. Oh yeah, a lot of you. Yeah, so many of you do the GEs first, and to a science faculty, it's the most frustrating thing that you can do. And unfortunately, there's it really depends on who your counselor is and who you see in the beginning, because STEM majors are guided differently, but that counselor needs to be specific to science to really have an understanding of the series, the scheduling, the rigor of the major. Yeah, yeah, I hear this a lot. Oh, okay, but waited to do physics and calc last. Okay, so for Nate, I'm interested in what your major courses are. Yeah, because yeah, yeah. Oh, chemistry. Okay, so you could take Chem 101, 102, and calculus. I mean, and inorganic and organic. The OChem classes. Yeah, that's totally true. That's the next common one, and that you did the right thing there, Nate, because chemistry is 4 courses: 101, 102, 211, 212. And usually in my physics 101 class, I see either the people who are just starting in physics and engineering or the end of the chemistry bio people. And yes, my physics course is a second or third priority for you, so that's correct. Yeah, okay. So, guys, again, I think we're going to have some time tomorrow to go into this in detail. Um, we're going to start lecture soon, but I'm pretty sure we're going to have tomorrow to go into deep detail. I'm also planning for a special guest to attend tomorrow. Yeah.
Okay.
But it all depends on us getting through. We have to get to a certain point in lecture today. So I have a guest on standby. So we'll see. We'll see how it goes. But I think I'm going to have time to answer any specific question tomorrow. Yeah, I think we'll have time. So I see we are over 20 people now, which is closer to our actual numbers. So I think we can start. And our goal today is to go into chapter 11 and cover angular momentum, which is going to be a complete transition of momentum into angular motion. Just like we saw all of our linear components into angular motion, the very last one is angular momentum. So I think we can get through most of it. We're gonna try. We're gonna try, and then I'll go over with the lab with you guys and show you some examples of some past submissions of the lab. Yeah, I think that's where we are for today. I'll give you an update on grading the exams. I'm almost done with exam two, almost done with exam two, and then I'll switch over to exam three right away. So I still think I can give you a clear update by Thursday, at the very least by the 30th, which I guess is Saturday or Friday. Yeah, and that's the drop deadline. So I still think we're on schedule for that. At least the first 3 weeks of classes, you'll have an update.
You I know
Um,
you commented on them before you put the grades in, so some people might not get the email. Like I got an email saying that I had comment on an exam, and so I
yeah,
checked it.
so all of that is fair. You can certainly look at it. There's nothing I can do to stop that, but I would wait, because as I grade, I make changes as
Oh,
I So you can expect your grade to be very close to what the feedback is on the exam, but it can change. So for some people, it actually did change yesterday. So, this is just to keep grades fair for everyone. I go back and forth all the time. But yeah, you can look at the feedback and get a look and estimate your grade based on that too. Yeah. Okay, I'm going to Okay, someone also remind me at the very, very end of class, I have an extra credit opportunity. It's a huge one. It's a huge one. So at the end of class, someone remind me. I do have the documents open. It's a good one. It's a good one. I do have the documents open, so I shouldn't forget. But in case I do, someone out there, ring the alarm. Okay, let me set up my screen and take us to chapter 11. I'm not sure if any of you have actually looked at the text for chapter 11. You may have noticed that I did things a little out of order. because I think they make sense. So the beginning of this slide set will be a little different than the order in your textbook, but the topics are still completely covered like we would normally see in a chapter, where we cover usually the beginning sections of the chapter. So that won't change. Let me get, oh, my chat screen. Okay. All right, so I have all my screens open. I can see you guys and your boxes and your videos, and I can also see the chat box, so feel free to use any one of them. I'm looking at all of them. So again, our goal today is to continue moving into rotational motion. And so what you see on the screen here is a satellite that is, you know, moving around Earth. And so now we can say a lot about the situation, right? We center the Earth's core to be our axis, our origin there. And so we can measure the radius or the distance from the center of Earth to the satellite. We could measure the angular speed. We can measure the angle. We know how to relate it to the arc length. And if we're given the tangential speed, then we know how to go back and forth. And so here's a quick summary of what we've done so far. We've gone and taken all of our linear components and transformed them into angular components. So position changes to the angle theta, velocity or tangential speed changes to angular speed, and acceleration, tangential acceleration, changes to angular acceleration. And all of these help us describe motion. And here are all of the equations that we've seen so far. What a nice summary of equations. So what you see here is our derivations for angular motion, right? And this helps us get from averages to instantaneous values. And then here we have kind of our translation. How do we get from some kind of linear measurement to then angular measurements, right? How do we get to linear to angular? And again, how do we get from linear to angular? So here we have this is our translation going from one to the other. And then we see our kinematic equations that are also a result of the derivations up here that we did back in chapter 2. So we can use these equations too, and we have some handy dandy conversions if we need to go from radians to degrees. So these all very nicely describe motion to us. And then what we did earlier this week was look at the cause of motion. And just like we did before, we saw that the cause of motion is a force. So we start with that definition of a force, and we look at its vertical component as it's rotating through some axis at some distance r. And we find that the cause of motion in angular motion can be defined as the torque. The torque is when some force is applied across some distance, and this is orbiting around some center of some sort. And with this, we came up with the rest of our equations in angular components. So here the torque is in linear components, and we took the definition of linear components, right? F equals ma, and we took that translation of acceleration in linear components and we changed it to our angular components, and we regroup so that we can describe the object's nature by its mass and where it's positioned, and that angular acceleration. And now we define this new component of the object, its mass and its position, as inertia. So inertia is the mass version in rotational motion. It's the mass, but it's rotating about some axis at this point away from the origin, some distance r. And so now we've gone from torque with linear definition to torque with angular definition, and we can use both. The last thing we saw yesterday was that because our torque depends on the inertia, perhaps you have different shaped objects that might have different masses, and that might affect the inertia. And in fact, it does. So we have our table with different types of inertia. And notice that for every shape here, we define what is the distance from the origin to the point where it's the outer edge of where it's rotating. And for each one of these, we can derive an inertia for its center of mass, so that it's modeled as this rigid object, right? A continuous object. And so depending on the object, you would use this center, this inertia in the equation right here. Okay, so that's where we got to yesterday, and we're going to try to practice this a little today. And this leaves us in our very, very last step. So now that we've looked at the cause of motion, can we now describe what is this motion? Right? Can we describe this and define torque in terms of what Newton thought motion was? And remember that Newton originally did not describe motion just based on position and time, but also based on the mass. So his original definition for motion was actually the momentum. And we see these are all linear components. So our goal is to try to define torque, our force here, in terms of momentum, and can we then take it to an angular momentum, a linear momentum and an angular momentum. So when we try to derive this, and that's what we're going to do next, is derive this equation, we really want to look at where in our torque equation can we find this velocity, right? The mass is going to be some known value, but where in our torque equation can we find this velocity? And you might remember that it's tucked into that force, because force is acceleration, times mass, and that acceleration is a change in velocity. So that's really where we're going to start. So let's take a step back and kind of look at the physics around us, right? What is it that we know, that we see, and how we can start making some observations about, or adding some math to our observations. So here's our first question. Anyone out there, y'all can tell me, when you see these Olympic divers and you see them go moving incredibly fast, how are these divers able to squeeze in 4.5 flips into 1.5 seconds? How in the world do they do this? Owen goes right away. He says, Owen says, just go fast. Duh. And then Keon says they bunch themselves into a small ball. And Randy says the same thing. They tuck, right? And Bradley, it is a lot of training and a lot of practice too, Nate. But what we're actually observing is what Keon and Randy said. We're seeing them tuck and get small. And we want to put some math behind that, right? Yeah, like skaters leaning into a spin too. What is it? What can we mathematically say about going from this spin to some small ball? Like, what is it that's actually happening? So let me just show you quickly this next clip. I'm going to fast forward it a bit. Yeah, out to, they spin out to leaning into a spin, and then they go out to in to speed up. Yeah. So let's see this next clip. It might be a little loud, so just kind of watch your volume on your screen. I don't know. Let's see. We don't actually need that. So this is an actual Olympic diver, and somewhere around here is where he'll eventually jump. But look at how quickly he's going to move. And try to see how many flips he takes, and when does he all of a sudden do that tuck? Okay, I think it's coming up. He is like 3 stories up. Okay, it's the last few seconds. Watch how fast it's gonna go. I just think that's amazing. That's so amazing to me. Oh, I missed it. That's okay. Let me try one more time. Boom. Wow. Yeah, to me that's just incredible. Yeah, that's a lot of practice. Yeah, and Nate tells us, oh, you saw a video about a figure skater and they actually have a special machine that spins them really fast to practice the spinning. Oh, that makes sense. You probably don't want to put yourself through the motion. I don't know. Yeah, he balls up before he falls even past the board. So right away he's trying to gain that speed. Yes, he did that almost immediately. We do need a slow-mo. Yeah. Okay, so let us look at just another example of this. And here's the one that Randy was mentioning to us. Look at what happens as the skater brings her arms in and closer to the axis, she speeds up even more. And so this is a really great example. We go from having our hands this far out to this, maybe this distance or so, and even smaller to at the top. So if we look at this mathematically, you might start to see that what we're reducing is this value r, right? What we're reducing is now a value r and a value r. So as we reduce r, we see that the speed increases. So we also see that there's no type of external forces acting on the person. This is starting to look like some conservation is happening here, right? Something is being conserved. Um, I don't know if it's Tanya Harding. I also don't know, Keon, if I don't know if this is revealing our age so much. Yeah. Yeah, for those of you answering, you're in a different age group than other people. I said this to someone about Tanya Harding, someone who was 22, 21, and they had no idea what I was talking about. But yeah, yeah. Randy, Randy says he was two. So yes, this is some sort of skater. You can attach any name to it, but yeah. Okay, let us take the same scenario, and now let's do some derivation. So again, I don't want you to necessarily memorize this or have to write this down, but just follow along with the math that we're going to do. Our goal is to go from the linear momentum to the angular momentum using the definitions that we've already had. So we are going to start with the definition of torque, and we came up with our definition yesterday, that it's the cross product of that r vector and the force vector. So we want to relate this to momentum somehow. So I remind you, what is the force in terms of momentum? The force in terms of momentum is the change in momentum, so that derivative. So let's plug that in. All I did was take this force here and plug it in here, and now we have this cross product. Well, we learned yesterday how to take the derivative of this cross product, and if you remember, the rules of cross product will tell us we have to distribute the derivative. So let's distribute the derivative. We'll take this derivative out here, and now this is what we're going to actually take the derivative of. So to distribute this across the cross product, I think you guys told me yesterday it's like the, what is it, the product rule, right? You take the derivative of the first, cross it with the second, plus the first. Oh, chain rule. Yeah. Foil. Oh, you guys are so good. I don't know these names. I don't remember them. As soon as you say them, I remember. Yeah. So we take the first and then cross it with the derivative of the second. Now, our goal is to look at this and see what we can say about it. In this situation here, when let's say this skier was skiing along, sees a pole, and all of a sudden grabs onto the pole and starts spinning. When she is spinning here, you are never going to see this radius change because she is attached to it with her arm, right? So her arm here isn't going to change lengths. In other scenarios, this might change, but in our model, in this model, this radius will stay the same. Oh, we're all a little rusty. Okay, I think we're saying it's the product rule. Isn't the product rule like a distribution? Chain rusty? Yeah. All of the above. We all know what we're talking about. So if this radius is staying the same, when you take the derivative of it, a derivative of a constant value here is going to go to zero. So if we look at that product right there, this derivative will go to zero because this radius is going to remain constant. So this product here is only going to be equivalent to this end, the second half of the equation. So we can just rewrite it and clear out this front half. And now we see then, all I did was bring it down, the derivative of this r cross p is actually the cross product of r with the change of the momentum here. And that's the cross product there. So we can bring this back and recognize that this r cross dp dt is what we have here. So this torque is actually equivalent to this here. Do we see that equation that they're equivalent? This is what we came up with. And the solution to this cross product is the torque here. So we can equate it to this d of dt r cross p. So if we rewrite it one more time, our torque then becomes the derivative of the cross product of r and p. Are we all okay so far there? I think so. All we did was sub things around, okay? So all we did was sub things around. This is equation 1. This goes to 0. We're left with this. We rewrite equation 1 down here. And you see that r cross dp dt is the value for the torque. So r cross dp dt is equal to the derivative of r cross p. So we just bring it down now. And here it is. So now we can say that the torque is the derivative of this is the derivative of this cross product. And this cross product is going to be our definition of the momentum crossing with some distance about some axis. This value here is what we call the angular momentum. So our angular momentum is the letter L, which is a vector, the letter L, and this is the cross product between R and P. And let me just remind you that this is very close to what we did before, right? Anytime we look at something angular, it's the linear component times the radius. So we get those same vibes. We take our momentum and now we cross it with that radius vector, and so we have our angular momentum. So let's take this over to the other side, and here is your formal definition in equation form. The sum of all of the torques then, or the torque, the total torque on the system, will be the derivative of R cross P, and we can now define this R cross P as the angular momentum. And so on the picture here, you can see we're centered at this origin, we're some distance away, and this is our particle. The distance away is the R vector. We apply some change in motion, and the result will be a angular momentum that is going to be upward, just like your change in motion in the bolt is going to cause the bolt to move up or move down. A question, where does the derivative go on the L1? Yeah, that's a good question. So literally this is the L and this is the L. So here you could write this as d of dt of L. That's the exact same thing. You could even put your parentheses there. I hope that answered your question. Yeah, so let us also get, actually that was gonna come up in a slide or two. Why is no L on the equal?
Like, why is there's no derivative on the L?
Here?
Like you're saying there's a, yeah.
This is the definition of angular momentum. The definition of angular momentum is the product inside of the derivative. The derivative of the momentum is the torque. So here we're isolating, yeah, we're isolating this new quantity that we just came up with, which is also the same way we derive momentum. We identify a new quantity, like what is this thing? We're going to define it as angular momentum. Okay, so again, the angular momentum is R cross P. The derivative of the angular momentum is the torque. So in words now, here it is. The instantaneous angular momentum L of a particle relative to an axis through a chosen origin O is defined by the cross product of the particle's instantaneous position vector R relative to that origin and its instantaneous linear momentum P. So here we're defining angular momentum in terms of linear components. Okay, it's okay for now. It's okay for now. Okay, so if we look at this, we can now start looking at an isolated system versus a non-isolated system. So here we have a non-isolated system, and so we see the sum of the torques are going to equal some change in angular momentum. A non-isolated system means something is going to change, right? If this were an isolated system, the change is equal to zero. But a non-isolated system, the change is equal to a number, to something. So non-isolated, the torque is equal to the change in the angular momentum. So torque is going to cause the angular momentum to change, just like we saw force causes the linear momentum to change. Very similar. But we just remember that this angular momentum L is defined as R cross P. And so we take our cross product rules and we then can find the magnitude, right? The magnitude of any cross product, we can bring in that sine theta. So the magnitude of P is mass times velocity. The magnitude of R is R, and we're looking at that vertical component of the momentum. So it's mv sine theta. We could also call this theta. And this also lets us bring in the rest of our cross product rules. If the position vector and momentum are parallel to each other and theta then is equal to zero, then sine of zero should equal zero. And so the angular momentum will equal zero here too. And then the opposite is true too. If the position vector and momentum are perpendicular to each other, meaning theta is equal to 90, then we will have MVR sine of 90, and sine of 90 is equal to 1. So the magnitude of the angular momentum here will just be the mass times velocity times radius. And again, remembering that these are linear components here, or velocity and radius are those linear components there. This is all fine. So the thing you just want to remember here is that we had in chapter 5 for an isolated system, right? This, or a system that doesn't have any motion or any change in its motion, the sum of the forces equals zero. If there was a change in the motion, the sum of the forces equal ma. So here, this is the non-isolated system. This is our version of the change in motion here. So this is what it would look like with our schematic that we've been using, that for the angular momentum to change, some external torque has to come in. If the angular momentum changed, it was due to whatever external torque came in. So a good way to think about it is that bolt. That bolt is not going to change or move unless you use a wrench, a torque wrench, and apply some torque on it, and then it'll change its motion. So this is the equation for a non-isolated system. The very last thing we want to do is get this into angular components. So we're gonna do this very similar to what we did in the last chapters and bring in our definitions, our translations, right, from linear to angular. So we'll start with angular momentum, and we'll say L equals MVR. These subscript i's are representative of any individual or instantaneous moment on this, in this scenario, in this disk. And again, this could represent, again, our tacos al pastor. And let's say you look at this piece of meat right here. It'll represent that. If you wanted to look at all of the meat, you would have to add up every single piece of meat here. So that's what the I means. It's an instantaneous individual moment in the system. So if we're looking at the angular momentum, we know the equation is mvr, and then we can take our translation for velocity, right? Velocity is equal to r omega, and so we put that in here. And then we do that regrouping again. We regroup so that we look at what is the object's properties, and then how is it moving on the angular in the system. So we have this value mr squared here again times omega. And then you can even ask yourself, angular momentum is turning about which axis here? You have your position vector moving with some velocity here along this circle. The angular speed and angular momentum here are each moving upwards. So they're all on the z-axis here. they're turning about that z-axis. It doesn't necessarily mean that they're moving up, but it can mean that they're turning about that z-axis. For example, like a merry-go-round doesn't normally fly up unless you look at like a UFO or something that's like a disc that's flying. Huh. Okay, I'll leave that out. I started thinking, I wonder if a UFO spins the other way to go down, but another conversation. Okay, so we look here and we remember that we have our definition there for mr squared, right? We sum up all the components along that z-axis, and this is just a specific example to this scenario. So the sum of all of the angular momentum components is the sum of all of the masses at a specific point, right? So here we have a mass at a specific distance. Here we have a mass at a specific distance. They're all moving with some angular speed. We sum all of them up, and this here then, or which is the same as this value here, mr squared, is that inertia quantity that we came up with this week. We have yeah, we should ask someone that claims they were abducted. Another example I just thought of too, what about our chairs, right? Could we rotate the chairs and move up versus turning the other way and move down? Yeah. Yeah. We could have a whole conversation about aliens. Anyways. Okay, so mr squared here is that value of inertia that we came up with. So now we have defined our angular momentum in terms of inertia, which is the angular mass, and the angular speed. And here, you know, we're all set there. You'll see that the angular momentum will also change around this axis too. So how it changes over time, we can then take that derivative if we wanted to, right? And here it is. What is the change of the angular momentum? The inertia will stay the same because it's the mass that's already constant, and the radius that we're spinning around stays constant. We pull that inertia out, and the derivative then just becomes the derivative of the angular speed. And so the change in angular momentum is equal to the inertia times the angular acceleration. Does anyone remember what is the change in angular momentum?
Torque? Oh, whoops.
Yeah, it's our torque, and there it is. So our change in angular momentum is torque, and now we have torque in terms of angular components. We went from torque being, what did we say, R times F, or R cross F, right? And now we have it in terms of completely angular components. And you can just remember here too that our angular momentum is also defined by inertia times the angular speed. So here what you want to do is really do your best to keep the track of everything. So if you saw the first few, if you were here when we first started, you saw these screens that I came up with, right? And I have one more for the inertia quantities. I'll try to show you that at the end soon. So it really becomes about keeping track of what are the definitions here, and you'll see quickly that, you know, it all makes sense. We just have to keep track of what everything is. This chapter focuses on angular momentum and inertia. So those are the ones you really want to remember here. Okay, let's see if we could try a question. We have a solid sphere. Oh, I don't see the time. Okay, a solid sphere and a hollow sphere have the same mass and have the same radius. They are rotating with the same angular speed. Okay, which one has the higher angular momentum? Yeah, you want to, and I see in the chat, you want to definitely brush up on inertia and momentum. Just keep writing the definitions over and it'll come to you. So here they're asking us, what is the higher angular momentum? So angular momentum is L. Okay, and we have two definitions of L. We have the mass times velocity times radius, or we have the angular momentum equals inertia times the angular speed. So if we look at what we're given here, they give us the mass, they give us the radius, and they give us the angular speed, okay? So let us see which equation should we use. This one we have mass, we have radius, we don't know anything about the tangential speed. This one we know angular speed, and if you remember inertia for a model, inertia for any particle, it's equal to mr squared. So in this case, we have mass and radius. So this is the equation you want to use. Now that we know this is the equation, we need to realize that we have a solid sphere and a hollow sphere. So we need to go to our inertia table, right? So let me write this here because I'm about to block it with the other one. So I omega. Oh, hell. I don't know why I thought it would be over it. If you need what was written, you can always look back at the recording and find what was there. Okay, so now we look at our inertia table, and this is a good example of when we need to use it. And we see that for a solid sphere, the inertia is 2/5 mr squared. For a hollow sphere, it's 2/3 mr squared. So we can now compare this. L for the solid sphere and L for the hollow sphere. Ah, okay, we have some answers already. Great. So for the solid sphere, inertia times omega, omega is the same in both cases. So we're only comparing, oh, we have new answers. Okay. We're only comparing the inertias now. So I should make that an approximate value. While I'm approximating, you guys can give me some responses because you're probably doing math really quickly in your head right now. Okay, I got my pen. So for the solid sphere, what is it? 2/5 mr squared. And then we'll just put the omega in. And for the hollow sphere, which is a thin spherical shell, this shell means it's hollow, we have 2/3 mr squared. Ah, okay, I see some new answers, great. And again, we just compare which one is going to be larger. And so here it's really up to you to figure out, is 2/5 larger than 2/3? And we have lots of changed answers here. We go from to solid to hollow to hollow. Why not just pick D? That's always okay too. And several answers of B from Daniela, Kian, and Andrea. And so, yeah, you'll see that 2/3 is larger than 2/5. And so your answer here is the hollow sphere. That's a good question that led us to using our table. Let's try another one. And here again, we're going to work with inertia and angular momentum. Yeah. Okay, let's try this question. There are no numbers. A father of mass m sub f and his daughter of mass m sub d sit on the opposite ends of a seesaw at equal distances from the pivot at the center. The seesaw is modeled as a rigid rod of mass big M and length L and is pivoted without any friction. Oh my God. At a given moment, the combination rotates in a vertical plane with an angular speed omega. Find an expression for the magnitude of the system's angular momentum. Okay, so before I go to this, let me just read Randy's comment. It's easier to spin a basketball than a solid foam ball of the same mass on your finger like a globetrotter. It has more angular momentum, so you can spin it faster. Yeah, you can spin it faster. That's true. That's a really good observation. And so let's highlight all the components first, and let's get to Daniela's question. So I'm highlighting all of the information they gave us, and the question by Daniela is, what do they mean by a rigid rod? Whenever we see that something is rigid, they mean that it has a continuous mass, or it can be modeled as having a continuous mass. Now, the reason this matters is because you guys remember when we draw our free body diagrams? And let's say you draw a free body diagram of a car. You model it as just a dot and the force is acting somewhere on it. But what you really don't know yet is that in engineering, the reason we model it as a dot is because we're considering this object as a continuous mass and the center of mass being somewhere in the center of the object. That is our model. So the continuous mass matters because we can use the center of mass as the center point of the object and all of the forces acting equally on the object. If we did not have a center of mass, the forces and the torques would be applied differently. You will see that as an engineer in maybe your junior level classes. Yeah, yeah. So it is important that we say a rigid object every time. Okay, so we have the mass of the father, the mass of the daughter. We know that they're equal distances. So if the full distance is L from here, and I'm just going to bring this down from here to the distance of the seesaw, we can say that that's L over 2 because they're equally far apart, right? Half of L. The seesaw is the object with a big mass M and length L, and everything, the entire system, right? A combination. The entire system rotates with omega. Find the magnitude of the angular momentum. So let me remind you that angular momentum is L. We're given this omega here. So this is our equation. And if you look at this, we need to know L. We are given omega as just a variable. So we don't know anything about inertia, but inertia is made up of masses and radiuses, radii, right? So how many individual masses are in this combination of a system? You guys tell me, how many individual masses are we given? Okay, I see 3. I see Doce. I don't I think that's a yeah. So okay, this I see a counter. Yeah, there are 3, right? There's the mass of the father, there's the mass of the daughter, and there's the mass of the seesaw itself. Randy, um, did you mean to say doce? Am I saying it right? Or doce?
No, yeah, that's what I meant.
Yeah, so here you can count the 3 individual bodies, right? And so when we look at the inertia of the entire system, remember, just like our taco meat, we need to add up all of those masses. So we need the inertia of the father, the inertia of the seesaw, and the inertia of the daughter on this side. So we come back to this side, and this is again what we're solving for. For us to get, and we know this, we know that value already, or we know the variable. So the moment of inertia, or just the inertia of the system, equals the sum of all of the inertias of the individual components, the seesaw and the 2 individuals. So the 2 individuals can be modeled as particles, as a body. So this one, for any individual, if you ever get an object like a bird, a person, a bag, I don't know, just any random object that doesn't clearly fit a shape, you can use this as the model. I equals mr squared of any particle. This might be useful for an exam, for example. Okay, but the seesaw, they told us to model it as a rod, right? So we go back to our handy dandy table and we look at what is the inertia for a rod. And here you see the rod rotating on like a horizontal surface, but this is a seesaw, right? Just flip that over and you'll see it rotating like a seesaw would. And so the inertia of the rod then is 1/12 ml squared, where L is the full length here. Remember that we are using little l, so that's what you're going to see. So let's add up all of the inertias. So the first inertia, 1/12 ml squared of the rod, mr squared, where r is L over 2, r is L over 2, and the next one for the daughter, mr squared, where r is L over 2. And Isla brings up a good question. Why not the inertia for a rectangular plate? Yeah, I could see that argument because the seesaw kind of looks more like a rectangular plate. The only reason is because the problem told us to model it as a rod. But I'm with you, Isla. I think that I think that this more closely looks like a plate. And here's why I think they didn't use the plate, because this is the top view of the seesaw, and usually this width is much less significant than this length. And so you can say in physics that this width is so small that is insignificant, and it can then be modeled as a rod. Um, that's, I think, their argument, that it is so small that it becomes insignificant. Yeah. That is why you chose engineering, Keon. You know, I can't I can't say anything. I must agree. I did the same. What is the practicality of this, right? If it were like a huge seesaw where the width would make a difference, then perhaps, yeah. Yeah, rounding does make more sense. When does rounding not make sense, everyone?
In the beginning of a problem.
Oh, yes, Randy, that's the correct answer. Absolutely. My joke of an answer was, yeah. Oh, it's too logical. My joke of an answer is that rounding does not make sense when you're trying to build a building that you don't want to fall, when you're flying a plane that you don't want to fall, when you're driving a car. You know, there are moments where you have to be very exact. This should also go back to why you shouldn't cheat, because if everyone cheats in Zoom University, all of the buildings around us are going to be falling in a few years. So don't do it. Yeah. Man, these, yeah, don't do it, guys. Okay, so while it makes sense to me that it could have been a rectangular plate, I think that's their reasoning, that the width is just not thick enough, right? Okay, so let us look at the the sum of the inertias here. The rod, this is the dad, which is the father, and the daughter, which I'm just going to write kid because it's shorter. And I want to remind you that this L over 2 is R, right? So you have mr squared. Oh, you guys are so funny. Yeah, yeah, you're right, Ren. Your comment in the chat. Okay, so we have this now, and all you have to do now is simplify this. Is simplify this. This might not look immediately to you like this, but let me just remind you that 1 over 12 is the same as writing 1 over 3 times 4. L over L squared, or the 1/2 squared, is the same as writing 1 over 4. And this is 1 over 4. So you can see that all they did was pull out the 1/4, and the 1/3 is left here, right? So we pulled out the L squared that's common to all of the inertias, and we pull out the 1/4 that's common, and we're left with 1/3. You guys wouldn't believe, when I was first looking at this problem, I don't remember, but when I was first looking at it, how many ways I tried to simplify it to get it to look like their answer. I did everything you could think of, and then I just realized, oh, 12 is 3 times 4. But yeah, I did all kinds of, I wrote everything over 12. It was dumb. Okay, so now we have our inertia. Yeah, it does make you stronger. um, well, now we have our inertia, and we just plug it into our angular momentum, and voila, that is our solution. L is equal to I omega. We got the inertia in terms of the variables that were given to us, and the constant angular speed that was also given to us. But this is a great example of how you need to sum up all of the inertias in the situation. Very nice, I think. Okay, so this is when you have changes happening. Now we want to look at the situation when there are no changes happening. I hope you guys are still okay. Let's try to see if we can go maybe 15 more minutes, and then we'll talk about a break. Let me put my timer on. Okay, good. Yeah, my legs are feeling it. I see all the thumbs up. Thank you, Ayla, Saja, and Daniela. So in about 15 minutes, we'll check. Okay, so what about when there aren't total changes? When there aren't any total changes, this is going to be an isolated system. So the change is equal to 0. in the system, there are changes happening, but as we look at the total system, we don't see any changes happening. So the total angular momentum of a system remains constant. The total remains constant in both magnitude and direction if the net torque acting on the system is zero. So the system would be isolated. And this is what it would look like. The sum of the torques are equal to zero. And remember, this is very similar to a static system where the sum of the forces equals zero. There are a lot of things that can happen in between here, but as a total, the sum of them will be equal to zero. So here, the derivative of the angular momentum, the total angular momentum, the derivative is equal to zero, which tells us that the change in angular momentum is equal to zero. Remember, this derivative is instantaneous, and this change lets us look at initial and final situations. And because of our practice now with conserved quantities, we can write this out explicitly, and we can say that the total angular momentum is constant, or we can say the initial must equal the final. And let me just remind you that this comes from L final minus L initial equals zero, and we just move this over to the other side. And so here you can start writing many components. And this, my friends, is the momentum that you're used to seeing. So when we see the figure skater with the large arms reduce his radius, and that reduction in radius results in a larger speed, is because angular momentum is conserved. There is no external torque coming in to act on the skier. The only thing that's happening is that the radius is reducing. If the radius in here, right, this is mr squared. If here you start off with a low radius. How do you start? High radius. You start with the high rate. I guess the picture is throwing me off. We normally start with our arms out and then come in. So I'm gonna, oh God, this is gonna confuse me.
Oh, he's going from fast to slow in this picture.
Thank you. He's going from fast to then stopping. Thanks, Randy. Yeah, so here he has a low radius, which is going to result in a fast speed. So he's going fast. We caught him mid-spin. And then it's the end of the performance. His radius, which is in here, mr squared, his radius is then going to increase, which must then result in a slowdown, which is the stop that we see. So notice that his radius here has increased, which must result in a slower speed, and he stops here. And the initial situation, he has a small radius, right? He has a small radius, which means he's spinning incredibly fast, and he's mid-spin, yeah. So here you see your conservation of angular momentum. You can take your values here and then just write them explicitly for initial and final. And then again, we can see it for our other situation where she's spinning, right? she's spinning at a slower speed with the arms out and then speeds up. This is what I'm used to seeing. Yeah, and the radius is ironically made up of mostly his radius. Yeah, that's true. That's so true. We can't extend that much far out, but it's so funny that that they're still linearly related, right? They're linearly proportional one to the other. Mach 3.
Like the bone, the radius?
Huh?
Like the bone, the radius?
Yeah.
Right? In the arm?
Yeah. Yeah, that's totally it. Yeah. Okay, so now we can really sum up just in general. You guys, just let me remind you of all of the conservation of energy and momentum and angular momentum that we've seen. The change in energy of a system, there's no energy transfer across the boundary. The conservation of momentum, there's no external forces acting on the system. And for angular momentum, there's no external torque, which is the angular force. So when things are conserved and it's an isolated system here, we get a lot of useful math. We can say a lot of things when we isolate a system to just the system. So it's to your benefit to to create that system too. Um, okay, it's 11:05. Let's try to go to 11:15 and let's see if we can try a problem here. Okay, so the formation of a neutron star. A star rotates with a period of 30 days about an axis through its center. The period is the time interval required for a point on the star's equator to make one complete revolution around the axis of rotation. After the star undergoes the supernova explosion, the stellar core is going to explode, which had a radius of 10 kilometers. It's going to then collapse into a neutron star of a radius of 3 kilometers. So it's going to go from a huge star during the explosion to a small star, which is the leftover of the supernova. And so the question says, determine the period of rotation of the neutron star, which is the final, the after effect. So let us just make sure we know everything here. It rotates with a period of 30 days, and this is the same period that we've worked with before. And let me remind you, I think, is this, I actually don't remember. Is this right? 2 pi omega? Speed is distance over time. Circle is 2 pi. Yeah, that looks right to me. That's a few chapters back, so let's hope that's right. Okay, so we have our period. Yeah, they spin incredibly fast. We have our period, and at this initial period, it has a radius of 10 kilometers, so that is the initial radius. And then it's going to have a final radius of 3 kilometers. Determine the period of rotation of the neutron star, so the final period. So the first thing you want to recognize is that there's no external forces acting on this system. When you have a supernova explosion, you literally have a collapse of the star itself. The balance of like pressure and temperature that keeps its shape is no longer there, and so you will have a quick explosion there. So this is going to be a conserved quantity. We also know that this is spinning about an axis, so we know it's angular. You might want to start with angular momentum and its conserved quantities. L equals I omega. And if we write this out, perhaps we can start thinking about like uh, what do we use here, right? If you look at the omega, you see that there's an omega in the period there. So that might be part of our key of how we're going to get started. So again, you have your initial equals your final components, and we can plug in what we know. So for omega, we have 2 pi over the period. Was that right? Did I write that right?
You did, yeah.
Okay.
Over omega.
Okay.
Oh.
I like you guys. Sometimes I really, if I'm not 100% sure, I really need someone to tell me like, oh yeah, that's right. Okay, so we have our initial period, our final period, and our initial inertia and our final inertias. And you can remember that the inertia, again, for any body here that you don't know the shape of, because you don't know if it's how solid it is, how hollow it is. You don't know anything about the shape of the star. Just model it with mr squared. So now we can plug that part into the inertia. So our inertia becomes the mass times the radius squared initial times 2 pi over the period initial, and the same thing for the final components. You see this value k here, and this value k here is just a constant that tells us the unique situation of the star. We don't know anything about the star, so it could be, 10 times larger, and that's where the constant k would go in. But it doesn't mean anything here. So this is just a constant. You can cancel that out. So here we have the mass of the star, the radius of the star initially, the radius of the star finally. You can already start canceling things out. The thing that we're solving for is this final period. So the 2 pi's cancel out, the k's cancel out, the masses cancel out, and it wasn't given to us, so pretty nice, right? And now you have just the radii over the period, and we can rewrite this and then solve for the final period. And so we're given the initial radius, the final radius, and the initial period. Now we can just plug everything in, right? And we plug everything in, the radii, the days, which was the period, and it does spin incredibly fast. And then we convert from days to seconds, and you see that the final one is only going to be 0.23 seconds. That's even faster, right? Even faster because it reduced its radius, and it physically makes sense that it reduced its radius there. Okay. Any questions about this problem? Okay, I have one more problem for you, and I think I can finish it in 5 minutes. If you guys can hold on, believe it or not, this last problem is the end of the chapter. So with that excitement, use that energy to just keep you here for 5 minutes, and then we'll take a break and come back. Okay, let's try this problem. A horizontal platform. Owen needs a break super bad. Owen, go take a break. Go, just go. Go and come back. I'll speak fast. Okay, a horizontal platform in the shape of a circular disc. Let me just skip that there. In the shape of a circular disc rotates freely in a horizontal plane about a frictionless vertical axle. This is a merry-go-round. Let's just say that. It's a merry-go-round. The platform has a mass m equals 100 kilograms and a big radius r equals 2 meters. So this is the big radius r, and a mass of the platform is 100 kilograms. A student whose mass is 60 kilograms is walking slowly from the edge to the center. Yeah. That's a good connection, Owen. If the angular speed of the system is 2 radians per second when the student is at the rim, what is the angular speed when she reaches a radius of 0.5 meters? So a new radius, let's say here, a new radius. So here you want to recognize, again, this is a system, and you want to think of that. You also want to start with angular momentum and think about angular momentum. L equals I omega will give us inertia and that angular speed. So we can think about the masses with inertia. So let me take you guys to the other side. So start off with writing the conservation of angular momentum for the system here. And if you start with the conservation of angular momentum, remember L equals I omega. Now all you have to think about is what are the masses that are involved. We have the mass of the merry-go-round and the mass of the kid, right? So the mass of the kid can be modeled as mr squared. I'm sorry, the inertia of the kid can be modeled as mr squared. But the inertia of the platform, the disk, has to be modeled as just that, a disk. So this is the solid cylinder or a disk. And notice that the height of the disk doesn't matter when we're looking at inertia. The way it acts at the top is the way it's spinning all around. So the inertia of the merry-go-round then is 1/2 mr squared. So we can write the two inertias here and the two inertias in here. The inertia of the merry-go-round plus the inertia of the child, the kid, I don't know what it's called. And so here it is. The inertia of the merry-go-round is capital M with the large radius. And the initial inertia of the kid, or the girl, is little mass m and big R because she starts at the rim. She starts at the outer edge of the merry-go-round, and then the angular speed initially is given to us. Then we equate this to the final situation. The final inertia of the merry-go-round remains the same, capital M and the radius capital R. And the final situation of the kid is now moving towards the center. And they gave us a new radius. And her mass remains the same. And then our goal here is only to calculate for omega F. So we just move the equation around, and we've pretty much solved it. Now we plug in everything they gave us. They gave us this mass, this large radius, this little mass, and this little radius, and this angular speed. And so there are all the numbers. And you'll see that the final angular speed of the child when they're moving in is 4.1 radians per second, or of the whole system as the child moves in is 4.1 radians per second. So that is your merry-go-round. And Owen makes a good point. This is one of those things at the playground that flings the kids off when it goes super fast. Yeah. Unless they're at the center, right? Unless they're at the center, they can hang on. So any questions about this problem? I hope it wasn't too fast. It was similar to the other problem. And the concepts here are similar to kinetic energy and the conservation of momentum. Yeah, I also think it's pretty straightforward, but any questions, please let me know. Okay, everyone's legs are probably frozen right now. We gotta get some motion in there. So let's take a break. How about 11:30? 11:30, is that okay? All right, I see a few thumbs up. Thank you. Thank you. Thank you. Cool. Okay, let's come back at 11:30. I'll see you guys soon. Hi. I hope I hope your legs are feeling better. Hello, Owen. Hi, Luis. Hi, Keon. Hi, Saja. Um, Welcome back from our quick break. I swear this one felt faster too. Hi, Robin. Um, yeah, it feels faster, but whatever. We're here. Hi, Ayla and Andrea. Welcome back. Um, is there uh, any questions about what we just saw? I want to if you have questions, please feel free to ask now, later, or in the chat. I'm gonna just pull up my summary slide that I made for this section so that you can see them. If you want to screenshot, that might be a good idea to do right now too. To take, let me see. Let me just start us off. Okay, I found it. Nope, I lost it. Where'd it go? Nope, I lost it. Okay, I found it. I found it. For reals, I found it. Okay. Um, Let me start this and just show you the summary screens again in case you want to copy them. It's a good summary, but you know, it's all from the slides, it's all from the textbook. There's nothing different there. So just one quick summary there. This is what describes motion. And then, oh, let me just give you a second in case anyone does want a screenshot. Um, this describes motion, right? Okay, I'm going to click to the next one. Here's the causes of motion and everything that we came up with here, right? And then our new one, now we can add in our causes of motion and inertia and angular momentum. And so that's what you see now here. Boom. There's everything. So you have, this is for non-isolated, this is for isolated, and then you have the definition of angular momentum. So taking torque from linear momentum to angular momentum, and then looking at a non-isolated system, and then looking at a isolated system. Okay, so now we can describe angular motion in terms of angular components. What I wanted to show you now is the lab. Should I keep the screen up for a little bit longer? Is anyone still using it? Okay, I hear nothing, so I'm gonna stop sharing. Okay. Okay, so let me take you guys now to our lab. That's what I said. Yeah, our lab. Okay, I hope this is the right one. Yeah, it looks like it. Okay, so let's go to the lab, and this is an at-home lab, similar to all the other at-home labs that you've had, where you get to describe what's happening around you. Okay, so this is the full assignment. It is due, as always, Friday by midnight as a PDF. Here, you are going to identify any two circular situations around you and describe the torque or inertia that's happening. In each scenario, you want to include a drawing with clear labels, include just a brief description of the object, its motion, and its physical features. So things like the mass, the radius, or any known speeds that you know. And then you want to include equations using the proper variables that will describe its translational and angular components. So things like the origin, the radius at which it's spinning, right, that final position, the torque, and or the inertia. And of course, if you're looking at these variables, you want to do them with respect to the angular components and some translational components if that helps the situation too. And that's it. That's the whole assignment, is to just identify two scenarios like you did before when you were doing units, And when you drew free body diagrams at home, now you're just going to look at circular situations. So I'd like to show you a few examples, but yeah, any questions about these 3 bullet points or anything about the assignment in general before I show you examples? Okay, let me pull up my examples. Okay, I have them all on the screen, and I'm just going to shift some things around so that I don't forget to tell you about the extra credit, so that I have that out too. Okay, so let me show you a few examples now of the lab. Let me show you some really good ones, 2 really, really good ones. Okay, let's start with this one. Okay, this is from last semester's class, and you see that the object here is the doorknob, and the description is just a round handle that you turn to open a door. And you see the way it's rotating on the screen. Let's see if I can make that a little larger. You see its rotation here, right? What is the clockwise and counterclockwise and the signs that are associated with it, and what type of forces you're applying, and the center axis, that dot is drawn in with the radius sticking outwards. And then you see that this is drawn right next to it at the top here, the same exact diagram with labels for everything. The radius here, the torque, and a force of friction that is happening there. And now we go down a little bit, and here's where you see the circular description. Okay, I hope this is large enough on your screen to see. So you have angular momentum in the equation and all of the variables and what they mean, and torque, and you see this now being applied to the torque counterclockwise of the doorknob. And you see this note here also. A typical doorknob has a mass of about 2 pounds or 0.91 kilograms, and a typical radius of 2.25 inches or 57 millimeters. And you can see the torque that's being applied, some force across some radius, and this is an applied force. So she specified that it's an applied force from your hand. And so this is a really great example of anything you see around you at home, and the doorknob is good. You could even use the door as a whole. And how it, yeah.
Is this example like within the lab?
No.
No.
No. The criteria for the lab is in the assignment, so I think that's enough. And Owen says, do we just do 1? No, you're going to do 2. So let me show you one more example. And again, if you forget that you have to do 2, you can just read the you can read the assignment, and it'll specify 2 scenarios. And yes, it is double the fun. Okay, now let's try this one. This one's also really good. And I should add that these are both A students. Okay, so here's our next one. It's a fidget spinner, right? And the fidget spinner, let me zoom into his picture. I think so. We have the hand showing the spinning motion, right? And then you see here the radius and the axis of which it's pivoting around. The radius here, and you see this 90-degree angle for the force that's perpendicular causing the motion, and you see the angular speed rotating about that axis. And we see that that is a torque because it's a change in that momentum, change in that angular momentum there. So this is a really great example of something too. And let me show you the rest of his assignments. So he then took this and modeled it over here, just like you saw in the last one, and put all the variables in. That 90-degree is really nice, the torque that's applied and the angular speed. We see the equations, right, going from linear to angular, the different torques that are involved. Now he took this and put it in a 3D graph, and we see the radius, the force, and again, the torque that's resulting, and a very nice brief description of it here. A fidget spinner, a person applies a force, it accelerates, which increases velocity, the angular speed, things like that. So that's another good example. I have another one that is pretty good. I would have liked to have seen a little more on this one, but it's pretty good. And everything that in the maths is actually written out in words. So um, you'll probably see the difference too. But I also think it's a really good example. So let me show you this one now. This is also another A student. So here, what is it, right? And it tells you it's a handmade traditional dice used for gambling in Cambodia or in Cambodian culture. And so you see that it is rotating about the Z axis that is starting at this origin, and you see the X and Y axis too. Here you even have that center of mass point, so you can just see what is the center of the object. The radius out this way, and you also see the radius out this way. You can measure the spinning either way, right? And then some applied force downward, that's just the force of gravity. And as you spin it, you cause this angular speed here. And so you have the equation for torque here, right? You have this equation for torque here, and then you have this explanation of what's happening. And the explanation is fine, but I think I would have liked to have seen a little bit more of these equations. But all of the components in the equation are labeled appropriately on the actual image there. You wanted the simplified diagram and on the graph, right? So the way that they did it was really clear, really simple, because they just pulled out the variables. You can do that, and that's a really good way to do it, by move everything onto a graph and take your actual situation and put it into like a graph. That's great. If you want to do it like this example where it's just drawn on the image, you can do that too. But notice that her visual is really good. And she also was able to use different colors to very clearly show the axis. So it's up to you how you want to show it. You want to kind of practice this, right? Yeah. So let me switch back to the last one just to make a point about it and how it really varies by person. So notice in this one, you can see the fidget spinner, but it's kind of hard to visualize the little arrows that are on here, right? So if I looked at this, I could certainly look in detail, but this down here with the graph is really nice. That I can see it much better. So in his situation, because the fidget spinner was drawn so small, it was better for him to bring it over to another graph. This graph shows us the vectors, and this one shows us the top view of the z-axis. So it shows us the circular motion that's happening. This one shows us the cross product in 3 dimensions. Yeah. So any questions?
This might sound a little dumb to say, but I noticed that like doing these labs help a lot with the test. Like they help understand the material to a different level. Like because you're drawing things and then you're like looking at other people's drawings of those things. So like to do what they did helps you like, it's like a deeper level of understanding. I'm sure that's why there's a lab component to the class, because doing is part of learning.
Yeah, and I was just having this conversation with 2 instructors yesterday. You guys probably know them, our engineering and one of our chemistry instructors, Dr. Diaz and Dr. Navarro. And we were having this conversation about the labs and how for exams, you learn the most when you do the labs. And it's so unfortunate that we're like on Zoom now because you don't get to see this stuff, right? But doing these type of labs, they actually mentioned my lab specifically. You get to learn a lot because you have to figure out how to draw it. And yes, guys, I do Beyond Labs is available for physics, and I was not about it. They have 1 or 2 that are really good for physics, like the spectrum lab, and the circuits one is a little okay, but they weren't for me. Yeah, they weren't for me. And for chemistry, it makes sense because they're really built out for them. And I don't know if they have another simulation that's as good as like our physics ones for PhET. But man, so I agree with you guys. And they were actually agreeing with these at-home labs that I've created for this class. So I completely, yeah, not a dumb question in any way. Yeah, I when you have to draw it out and really think about it, it's really cool. And let me tell you guys, I've seen some crazy things from these labs. My favorite circular motion one, I didn't get a chance to pull it up because it was from 2 classes ago. um, a hydro flask, and the student took the hydro flask and drew the whole flask, but the top of it, think about when you have to apply a force to open that hydro flask, especially if it's under even a little bit of pressure, you really got to nudge it, right? That's a derivative. That's a change in motion that you're causing. And so he drew the hydro flask out beautifully and drew the angles, and it was great. Oh, and Keon, your girlfriend is doing Beyond Labs and it looks really bad. Yeah. We're working with what we got, man, but they weren't for me. So I've seen the hydro flask. Another cool one that I saw was like on the Apple Watch. There's like, or
Oh,
any watch,
wow.
right? Has the little, yeah, the little crown spinner thing. Someone used that. I saw someone else use the wind. What's the thing called? The fan.
Ceiling fan?
The ceiling
The
fan.
wind?
Yeah.
The wind maker.
What?
The wind maker.
Thank you for translating. um, it's so funny when I traveled abroad, I was really good at talking to people because the way I describe things is not the way that it's normally done in English. But in other languages, they understand me. Yeah, the ceiling fan. I don't know. You guys, maybe some other cool examples you can think of. Um, but look around
Blender.
your house, huh?
The blender. Oh, especially the blenders that make heat. They make heat because they spin so fast.
Yeah, yeah, that's exactly it, right? Then that's I don't think that's a conserved quantity, right? Because the energy is transforming to something else. It's still very valid here, but yeah, that's really cool. That's another cool one.
So it's not an automated system.
Yeah, it's not. It wouldn't be. I guess it wouldn't be because you're creating that change. Um,
It depends on your perspective of the system.
yes, if we're looking at the change in energy, it can still be conserved. Yes. Oh, some good ones. Computer fans. Yeah, those computer fans and the knob, any knob on any appliance, but the espresso maker specifically. That one, that's an awesome example. The last thing we had Labster for simulated labs in the chem class I took last
Oh,
semester,
wow.
and it was pretty. Oh, okay. I think when I said Beyond Labs for physics, I think I meant Labster. But there was two that I kind of liked for physics.
The lab is the one where you have to go in and wash your hands and put on the lab coat and stuff.
Yep, it is. Yeah.
I'm not a fan of those. They're rough. And sometimes they don't explain like the next thing you're supposed to do, and like you get stuck like just because you don't know what they're wanting, and sometimes like you try to click on something and it won't let you do it, but it won't say why.
I also think that they look really funny from the videos too, Saja. When this whole shutdown happened, um, we were given like, that fake spring break they gave us that they extended for 2 weeks, but it was not spring break for faculty at
I was
all.
still hopeful back then.
Huh?
I was still hopeful back then. Thought we were coming back.
Me too. But those 2 weeks were horrible because all we did nonstop was try to convert everything so you can do online. And I went to so many like Labster and Beyond Labs like talks and looked at so many simulations and tried them all. And not for me. So, here I am making FET and at home simulations for everything. So it's cool. For some people, it really works,
And my instructor for those, he graded us on like the points you received on the labs, or not the completeness of it, but like the points you got on it. So I had to do them like 4 and 5 times sometimes. But after I did that a couple times, I remembered to just write down all the answers on a paper and then like go in and do it.
that was one of the benefits that I could never understand. I got that there was point systems, but the questions and it just didn't agree with the way that I lecture. So maybe I needed to look more into it. I don't know, but I hear what you're saying. I remember that I thought that was the only reason I thought maybe I should try this, because if it grades up by a point system, that would help me a ton, you know. But nah, not for me. Owen says, yeah, some professors still don't know what they're doing online. It sucks. Bear with them. There's so many instructors that I don't know how they're doing it with only one monitor, like only one their computer. I don't know. Um, yeah, all the clicking on Beyond Labs. Yeah, yeah, I totally get it. It's
Like
fun.
if you make one wrong click, you get points taken off. Like if you just happen to drop the object or something, you get points taken off.
Well, it's better than in lab, right? If like you drop it and
Yeah,
then
you
there's
die.
then there's like fire. Oh, the tritation labs. Damn. Yeah. You know, to be honest, the titration labs suck in person too, because one little drop and you're off. It's completely wrong, you know. So yeah. Okay, in Labster they were a little better. Wow. Yeah, see, I'm not even gonna go trying to pick either one. Okay, so you guys got the lab for this week. It is Wednesday and they're due Friday, so get creative with it. You have 2 situations you can come up with. I challenge you, do not be basic. Do not be basic. Go find something interesting and try to figure out its circular motion. Use the internet to get some inspiration. If you find an object that you think is cool and you don't quite understand the circular motion, do a little research online. I'm sure there's something out there that'll help you make it all click and make it all work. Yeah, try something cool. Ah, titration labs. Andrea's our chemist. I see. Okay, so this brings us to a nice smooth transition into the extra credit opportunity for this semester. So extra credit, let me just give you all my stance. Extra credit is not something that you should depend on ever. And it should not be something that you think of as, this is how I'm going to get an A. Mm-mm. Extra credit is extra, right? You got to do the credit first and then you get the extra part. So this extra credit, normally my extra credit is 1 to 2% on an exam. This is never before. This extra credit is worth 0.5 to 1.5% of your total grade. Total grade. So if you have an 89%, this is the one opportunity you have to bump it into a 90.5. So what I would like you guys to do as an extra credit opportunity is try to attend a science event this weekend that I'm about to show you. So let me put this out there and then we can talk about it.
So 1.5% of your grade. So like if you have a 90%, you would have a 91.5 max or a 90.5 max. And I believe if it's a 90.5, that would be a 91.
I'll give you more details. Just let me tell you what the event is. And yes, of course, the event is all on Zoom. And here it is for all you science majors. This is a research conference for you guys, and it's going to happen over the next 3 days. This is brought on by the Alliance for Diversity in Science and Engineering, and it's a young research conference, young researchers conference, which is you guys. So you're going to see students at all levels here presenting science, from community college to upper division students like juniors and seniors to masters and above. And it's going to take place starting tomorrow from 12 o'clock all the way through Saturday. Every day there will be short speakers. It's not too late to register, Owen. I'm going to give you a new link because we emailed the guy last night and he gave us a new link just for you guys. So
like an Eventbrite thing? Is it on Eventbrite?
no, I'm gonna give you the link. Give me a second, guys. Y'all hold up. let me finish my pitch. Okay, let us look at I'm gonna show you a quick agenda for it. I mean, I guess if you guys are already interested in the link, that means you're down. So that's good. Let me set up the.
I feel like you just offered us percentage points. I don't think anybody's not down. Even if you have 100%.
I agree. I
Extra
agree.
cushion.
I think this is, and again, I never give full grade percentage extra credit. I give, oh hell, I only give 1 or 2% on an exam. Okay, so we also got the brief agenda, and here's day one. Okay, hold on a second, I'm gonna move it. Okay, I think you can see it now. Okay, so this is day one. Look at the keynote speaker. It starts around 12 to 5, and this is a longer one. A professor of engineering from the National University of Colombia. Again, this is a U.S. event, but from Zoom, you can go all around the world right now. And we have student talks. All of their research from all different places all around the world. University of Ghana, Texas A&M University. This one's all chemistry stuff. And as we scroll up, to day two, or continuing day one from 3 to 4, health IT data specialist from different companies, right? Or a grad student talk from UC Davis, someone from Johns Hopkins towards materials discovery for quantum applications. These are people that are just a few years ahead of you guys, very much where you're going to be. So go see, right? Another one from the University of Pittsburgh, drug development.
Oh, I'm from there.
Yeah. Okay, let's go on to day two. Again, it starts at 12. This is on Friday. And so our keynote speaker is a professor of biochemistry. Notice that these keynote speakers are specific people. They're on the younger side, so someone that you can hopefully relate to a little bit more and find out about their journey too. Every keynote speaker always talks about their journey to where they are now. So that's something to consider, or just go listen. Student talks 1 to 2. Again, University of Tennessee, Vanderbilt, Cornell, different places. Moving on with day two, now a keynote speaker, bioengineering, right? Another chem grad student, some postdoc students at Yale. So postdocs would be cool to figure out that process. And then we have day 3 is Saturday, and it moves to the evening time. So this is for all schedules, right? Now look at this. There's a social, so you can actually talk online with people from different backgrounds. And there's a community college panel from 7 to 8 p.m. on Saturday. You have, of course, a moderator and then speakers, PhD student panelists. And you guys, let me tell you, if you go there, someone say hello to this person. This person, Dr. Brenda Andrade, did the master's program with me. So she was in my master's program at the same time. She was pursuing a master's in chemistry, and I was doing the master's in physics at Cal State LA. So now I think she's postdocing at UCSD. Yeah, and she's had amazing journey too. Her PhD was at, I think it was University of Illinois, a very prestigious university also. So we have some great events. What I'm gonna do is put the registration link right away into the chat that we got especially for us latecomers. But I'm also going to create the assignment on Canvas. And let me tell you what you have to do to actually get the extra credit. You have to attend 3 talks. For each talk that you attend, you will be given 0.5%. So if you attend 3 talks, you will get 1.5% credit for your whole grade. And what you have to do is just write a paragraph about the science that you learned in the talk. You should include in any way some evidence. I suggest a screenshot of you being in the window or you being there, any way that you can. Okay, so let me put this link in the screen, in the chat, and there it is. I'll actually click on it and show you what it looks like for those of you. Oh, I already responded. I can't do it again. Oh, maybe if I go incognito, huh? It's okay. You guys just click on it. Register. It's super quick. Also, if you can put that you got the link from Trade Tech, that's better for us to give you more opportunities. But you could put your homeschool. I don't really care. As long as they know you're from the LA Community College District, I'm happy. But yeah, you're going to see like 3 of us professors are giving it to all of our students. So you're going to see a whole bunch of trade tech people, maybe even each other in the talks. Yeah. So again, 3 talks, any talks that you want, a small paragraph summary of the talk, what you learned in the science, and some sort of evidence like a screenshot. Yeah. What was I going to show you? Was I going to show you anything? I think I got it all. Anyways, I've registered. I'll try to attend some too. And yeah, they're all at different times. So try to attend. Tell me about it. You'll submit 3. Or if you can only go to 1, at least that's 0.5. If you can go to 2, that's 1%. If you can go to 3, that's 1.5% that you'll be adding to your grade. So consider that. I think you'll have a good time. And in my engineering 101 classes, I normally send all the students to a bunch of events too, and they always come back with real positive feedback. You know, it's good to learn about what you want to do. You know, see yourself. What is the organizational email for trade? You can just use your LACCD email, I think. And from your LACCD email, I think that should be enough. I think they'll just ask you where you're from, right? Yeah. Let me see if I can just open it incognito really quick.
Your organization and your email, the organization's email.
Ah, okay.
So like your email from the organization that you're affiliated with.
Oh, that's dumb. Just put LACCD email. It's the same thing as trade.
Yeah, that's the organization that we're affiliated with. That's our email.
That's right. Okay, let me see if I can sign in with this. Oh man, this is so dumb. Incognito is not letting me go incognito. That's all right. Anyways, yeah, or yeah, if you have any questions, let me know. I'll stay on if you have any questions about this or anything else. But really, really wonderful events. And in the spring semester, as these events come to us, I will share them. And also, sometimes I'll offer extra credit, not always, because these are to your benefit to go to. So without extra credit, you should go anyways. But look through the talks, find something that is similar or close to what you want to do. And if it's not close to what you want to do, maybe find someone at a school that's presenting from a school that maybe you'd like to attend in the future. Because, technically they're a representative of that school. Yeah, that's all I got for you guys. Yeah, you're welcome. I'm really glad you guys are super interested. You're going to see Dr. Diaz's chemistry students there and some of Dr. Navarro's engineering students there too. So, yeah. Yeah, I'm glad you guys are going to go. And in the spring, I'll share a whole bunch more of these events. It's really fun. Okay, that's the end of my show. Tomorrow, come back. We're going to have a really good talk tomorrow. And by me, it's me always talking, and special guest, hopefully. Special guest is towards the end of the class. We'll see if that happens. I hope it does. Yeah, any specific questions that you have about transferring in school and all of that, get them ready for me. We can talk about it tomorrow. Oh, and special surprise guest. Yeah. Okay, guys, that's all I have. I will stop recording and lecture for today, and keep a lookout on Canvas. I'll put all the information on Canvas if you missed it, and I'll see you guys tomorrow. Not a celebrity guest, I wish. Although Trade Tech has had every celebrity you could think of, because Trade Tech is central to LA. That's why. Bye guys, have a good day. Bye Scott, bye Owen, bye Jake, bye Isla. Bye.
Thank you, Professor.
Yeah, no problem. Bye Keon. Bye everyone.
Hi.
Bye, Michael. Bye,
Bye.
Randy. Huh?
Can I ask a question?
Yeah, of course. Let me just stop recording. I don't know where my button's at.